this case, I have underlined some of the givens. I know that x is always 500 feet, so that's a given. I'm going to want to use that in my equation if I can. At an instant, I know that theta is pi over 8, and I know the change of that angle theta with respect to time is equal to 0.30. So because we have an angle here, this suggests that I either want sine, cosine, or tangent, and I'm interested in how fast the balloon is rising. So dh dt, the opposite, seems to be important, and I've been given the adjacent of 500. So the equation that will deal with opposite and adjacent is tangent, so that's the one I'm going to use. So my base equation is tangent of theta equals opposite, which is h, over adjacent, which is 500, and that's a constant. Now I'll take my derivative with respect to time, and I'll have the derivative of tangent is secant squared theta times d theta dt equals, well, the derivative of h over 500 will be 1 over 500. That's the constant times dh dt. And this dh dt is the thing I want. So that means all I really need to do is multiply everything by 500. And I'll have dh dt equals 500 times 1 over cosine of theta. Well, we know our theta is pi over 8, so I'm going to plug that in. I can square that whole thing because secant is 1 over cosine squared, and that will be my answer. In this case, I can just go right to my calculator and figure out what cosine of pi over 8 is. I'll do that now. Well, my cosine of pi over 8 is this 0.924 right off my calculator. I square it, I get 0.854, and then when I do 1 over that, I get 1.172. That's the number that I want. So I have 500 times that 1.72 gives me a dh dt of 585. I'll stick with my 3 decimal places even though we didn't say. 786. And I'm looking at feet per minute because our distances are measured in feet and our times are measured in minutes, so we'll have feet per minute as our units.